Good day everyone, welcome to ARARAO Tutorials. In this video, we will solve again a fluid mechanics problem from the book of Yunus A. Sengel and John M. Simbala, Chapter 6, Momentum Analysis of Flow Systems. So, this is a review problem 6-96. A water enters a mixed flow pump actually at a rate of 0.3 cubic meter per second and at a velocity of 7 meter per second, and is discharged to the atmosphere at an angle of 75 degrees from the horizontal, as shown in the figure below. If the discharge flow area is half the inlet area, determine the force acting on the shaft in the actual direction. So in this problem, our given are Q is equal to 0.3 cubic meter per second, and our angle is 75 degrees, and our velocity is equal to 7 meter per second. So for our solution, water enters a centrifugal pump actually at a specified rate and velocity, and leaves an angle from the actual direction. The force acting on the shaft in the actual direction is to be determined. So our assumption in this problem is that the flow is steady and incompressible. So the forces acting on the piping system in the horizontal direction are negligible. And the atmospheric pressure is disregarded since it acts on all surfaces. So water flow is nearly uniform at the outlet, and thus the momentum flux correction factor can be taken to be beta is equal to 1. So our properties, we take the density of water to be 1000 kg per meter cube. So our analysis from the conservation of mass, we have mass flow rate 1 is equal to mass flow rate 2 is equals to mass flow rate. And thus, V1 is equal to V2. And AC1 V1 is equal to AC2 V2. Nothing that the discharge area is half the inlet area. The discharge velocity is twice the inlet velocity. That is AC1 V2 is equal to AC1 divided by AC2 times V1 is equal to 2 times velocity 1 is equal to, substituting the values given, we have 2 times 7 meter per second. We get 14 meter per second. And for the pump, we take the pump as the control volume and the inlet direction of flow as the positive direction of x-axis. The linear momentum equation in this case, in the x direction, reduces to the summation of forces is equal to the summation of beta mass flow rate times velocity out minus the summation of beta mass flow rate velocity in. So we have negative Frx is equal to mass flow rate times velocity 2 cosine theta minus mv1. So we get Frx is equal to mass times v1 minus v2 cosine theta. So where the mass flow rate is equal to density V is equal to 1000 kg per cubic meter times 0.30 meter cube per second or cubic meter per second. Calculating this one, we get 300 kilogram per second because this cubic meter will be cancelled. And substituting the known quantities, the reaction force is determined to be reaction force X is equal to 300 kilogram per second multiplied by 7 meter per second minus 14 meter per second cosine 75. In order to convert this to Newton, we have to multiply it by 1 Newton over 1 kilogram dot meter per square second. So we get 1013 Newton. So this is our reaction force, 1013 newtons. This is our final answer. So note that at this angle of discharge, the bearing is not subjected to any horizontal loading. Therefore, the loading in the system can be controlled by adjusting the discharge angle. So that's it for today's video. Thanks for watching. See you again on our next one. Happy learning!